Another common way to talk about exponential models, specifically that describe exponential decay, that is, an exponential function that is decreasing, is the concept of the half-life. This is especially common in science. The half-life of a substance is the amount of time required for half of the substance to go away and the other half to remain. So it's the time required to multiply by a half. If we're told that a certain radioactive isotope has a half-life of 183 days, and we obtain a 50-gram sample, that means the starting value of our mass is 50, and that happens at t=0. A 50-gram sample is obtained, means we start out with a 50-gram sample. The multiplier, because we're talking about the half-life, the multiplier will always be 1/2. If we're being given a half-life, the multiplier is a half, and then the half-life is just the time it takes to multiply by a half. So we'll multiply by a half every 183 days. Our delta T is 183. So our mass, we start with 50, and then we multiply by 1/2 to the power. So our starting time is 0, so we'll just have T, nothing to subtract, over 183. So that's how we use the half-life to build a model. We can use this model to answer questions. So maybe we are told that we have an isotope with a half-life of 183 days. We obtain a 50-gram sample. That was the same information that we had before. And now we want to know how much will remain after 1 year, which is 365 days. Well, that's just saying that T equals 365. This is the same information we had before, so we're going to have the same function we had before. We want to know how much is left after 365 days. That's just asking us what is m of 365. So we can just throw that into the calculator, right? M of 365, that'll be 50 times 1/2 to the power 365 over 183. So we say 50 times a half to the power 365 over 183. And of course that's some awful decimal. We're told to round to 2 decimal places. So we have about 12.55. And so our answer, right, we've just found a mass. In this problem, our masses are measured in grams. So our answer will be 12.55 grams. 12.55 grams of a radioactive isotope remains after 1 year. Sometimes we're also asked to compute the half-life when we have an exponential model that's described in some other way, usually in terms of a percent change. So in this example, a drug is metabolized by the body in such a way that the amount of the drug in the patient's system decreases by 22% every hour. We want to know what is the half-life of the drug. Okay, so this is tricky. Why is it tricky? Because we are not told a starting amount. Let's see what happens though. We have decreasing by 22%. So our multiplier is going to be 1 minus 22%, so we get 0.78. We'll call the amount of the drug D. The amount of the drug after T hours is whatever we started with times 0.78 to the T, right? We lose 22% every hour. So we want to know how long it takes for only half of the drug to remain. In other words, we want to know how long it takes to have a half times D0 left. Oh, we have an equation with a D0 on both sides. As long as we don't start out with none of the drug, as long as D0 is not 0, and if it was, this question is silly, we can divide both sides by that number. And we get 0.78 to the T equals 1/2. Well, we know how to solve that. T is the log base 0.78 of 1/2, or the log of a half over the log of 0.78. Again, we're told to round to 2 decimal places, so we'll say log of a half over log of 0.78, and we get about 2.79. Okay, to give our answer, we need to figure out what the units are. We're losing 22% every hour. We just found a time. Our time is measured in hours. So the half-life is 2.79 hours.